around, I don't know, 15 years ago. It turns out that it has many nice combinatorial properties and many nice combinatorial characterizations. I will give you probably the easiest to state. For every radius r, there exists a number t that can depend on r, such that every graph from my class excludes R subdivision of KT. Yeah, so let's draw it. And R subdivision of KT is, if T is equal to 5, would look like that. So take a clique of size T and subdivide every edge so that it becomes a path of length R. And I would like to exclude this structure as a subgraph. Yeah, in all my graphs from T. So in particular, for R equal to 1, there is some bound on the sizes of cliques that I exclude in my graph. For R equal to 2, there is some bound possibly larger for the sizes of one subdivision of cliques that I do not see in my graph, and so on and so on. So in particular, again, being nowhere dense, generalizes excluding a minor, right? Because if I exclude some clique as a minor, if I exclude some H as a minor in particular, I exclude some clique as a minor, then what then? For every possible R, I do not see such a structure of size larger than this clique that I exclude as a minor, right? Because this thing you see here, this clique as a minor. Good. So maybe these are the examples, and I will now draw those examples in kind of a lattice way. And I would like to reserve this board here for a particular diagram, which I believe is the most important diagram of this talk. So here are classes of bounded trees, right? Here, a more general concept are classes that exclude a minor. Here are classes that are nowhere dense. Yeah. Here I will also put a box just for reference. There's a concept called bounded expansion, which on one hand, which is between excluding a minor and being nowhere dense. It is closer to being nowhere dense in the sense that you exclude certain structures that are sort of local, in the sense that they are there are structures with this kind of length at most R, and not like minors with unbounded length, right? Good. And of course, if you have bounded tree width, you can also think about more restrictive notions of structure. You can have bounded path width, so graphs that are path-like. And if you are also a fan of tree depth, then you can think about graphs of classes of bounded tree depth. Yeah, so these are the tree decompositions of bounded depth. Good, so this is kind of a hierarchy of sparse graph classes finishing on this notion of nowhere density. So why do I say that we finish at the notion of nowhere denseness? This is because in some sense, in the sense that we are interested in this talk, this is the limit, or say, from the computability point of view, a limit of sparse graph classes that are tractable. And what do I mean by tractable? I mean tractable with respect to the problem of model checking for first order, right? So FO model checking. This is a computational problem that we are interested in throughout this whole project. And this works like that. So the input to the problem is a graph G and a sentence phi of first order logic on graphs. And I just ask, the question is, if phi satisfied in G. Yeah, so is G a model for phi if you are into model theoretic terminology, right? So this question alone, if you think about a brute force solution, what I can do, I can just brute force all the quantifiers in phi. Whenever in phi I'm trying to say there exists a vertex, I just branch into all possible vertices that are there. Yeah. If there is for every vertex, I just again branch into all possible evaluations of a certain variable. So the brute force algorithm for this runs in time the size of my graph, let's say the number of vertices of my graph, to the size of the formula. Yeah, because I may have multiple quantifiers stacked on top of each other, nested in each other, and each time I'm branching into n possible quantifiers. Yeah. So we would like to understand when and under what assumptions we can get a better algorithm for this. And in particular, we'll be interested in getting fixed parameter tractable algorithms. So not going into the details, I will just now tell you a theorem of Martin Grohe, Stefan Kreutzer, and Sebi Sibet that says the following. So imagine that I've got a class of graph C that is nowhere dense. Then first order model checking on C can be done in time some function of the formula of the sentence times the size of the graph to the power 1 plus epsilon for any fixed. So in other words, instead of having the degree of the polynomial depending on the formula, on the sentence, I actually have almost linear time in the sense of the size of the graph. It's just the multiplier that depends on the property that I'm trying to test. Right. And this kind of algorithm where the exponent is independent of the parameter, which is the formula, these are called fixed parameter algorithms. And we would like to understand when and why first order model checking can be solved in FPT. Good. So that's the theorem of Grohe, Kreutzer, and Siebert. And the nice thing about this theorem is that actually it is in some sense tight. So moreover, if C is not nowhere dense, but subgraph closed, then FO model checking on C. Just mentioning, FO model checking on C means FO model checking restricted to inputs coming from the class C. Yeah? Then FO model checking on C is as hard as on generators. Which, if you are into parameterized complexity theory, this is AW star hard. So this is very nice because it tells you that from the point of view of this basic algorithmic model theory problem of model checking first order logic, nowhere denseness is kind of a limit of what we can do, right? At least as far as subgraph closed classes are concerned. Yeah, if your class is nowhere dense, then you can do first order model checking efficiently. Otherwise, you are as hard as generators. Good. So the question is it the end of the story? And of course it's not, because otherwise I would not be standing here, because there are classes that where first order model checking is tractable, but are not captured by this simple picture here. For example, I could think about classes of bounded click width. I will not give you a definition of click width. It is a parameter that generalizes tree width. So every class of bounded tree width has also bounded click width. It is a sort of tree-likeness parameter for graph, but tree-likeness rather modeling the graph in an algebraic way rather than in a topological way as tree-width does. So in a sense, a clique decomposition or a clique expression of a graph sort of builds the graph from smaller pieces using some kind of algebraic operations. And this is a parameter that is suitable for treating dense graphs as well. For example, cliques themselves have clique with something like 2. And because it is a tree-likeness parameter, it comes with certain decomposition on which you can employ dynamic programming, bottom-up dynamic programming. And using this kind of dynamic programming, you can solve model checking problems for first-order logic. And the reason why the tractability here, let me just say that FO model checking in time some function of the formula times n squared. Currently it's n squared. The reason why this falls out of the regime of the theorem of Gora-Kreuz and Siebert is that these classes of bounded clique width are not subgraph closed. If you take cliques and you close them under being under subgraph, you suddenly see all the graphs. Yeah. So this means that this theorem is not the end of the story, because this property of subgraph closures is actually a really strong one. It really makes us miss a lot of interesting classes of graphs. Okay, so let me continue drawing this diagram. If you think about bounded clique width, then there are also notions of bounded linear clique width, which correspond to path width, and of bounded shrub depth, which correspond to tree. I will not define these notions. I'm just showing you that here there seems to be another line of properties of classes of dense graphs that sort of mirror the properties of classes of sparse graphs. And actually, if you look at this, there is a nice way of going from this row of the diagram into this row by restricting attention to so-called weakly sparse classes. So a class C is weakly sparse if there exists a T such that KTT is not a subgraph of G for every graph G in my class. Yeah. So in other words, these are classes that are biclique free, that exclude some biclique as a subgraph. Yeah. So now the nice thing is that actually, if I take the property of having bounded clique width, and I additionally assume that the class is weakly sparse, then I get exactly classes that have bounded tree width. And the same goes for linear clique width, and the same goes for shrub depth. So in a sense, there is a generic way of going from this row so far to this row by restricting attention to classes that are weakly sparse. Yeah, so this is already quite nice. If you follow recent work on structural parameters for graphs, you probably know that there is also a notion called bounded twin width. I will not define this notion here, but on one hand, it generalizes bounded clique width. But it is a parameter that is not really about tree-likeness, in the sense that, for example, every class excluding a minor have bounded twin width. So in fact, here you can put another box called bounded sparse twin width, which stands between bounded expansion and excluding a minor, which is exactly the projection of bounded twin width to weakly sparse classes. And again, with some caveat of that we do not know how to compute certain decomposition for twin width, first order model checking can be done in linear time on every class of bounded. Right, so far, this is a nice diagram, but there is a hole here in the bottom right corner, right? So we would like to understand what are properties of graph classes that are general enough to capture nowhere denseness and should still allow for efficient model checking of first order logic. Yeah. So what should be the sort of dense analog of nowhere denseness or the dense analog of bounded expansion? Yeah. What to put here? So this is what this talk is about. And the idea is to try at least to have a basic guess at what should be there. And this guess will be based on description through logic, through obstacles in logic, describable in logic, and then try to derive some combinatorial characterizations of those classes. So in order to define what will be there, which will be called monadic stability and monadic dependence, I need to tell you how to describe or how to describe the graph classes in logic and how to define obstacles in logic in particular. And this will be about so-called first order interpretations or first order transductions. So a first order transduction, or just a transduction, is a way of taking one graph and transforming it into another graph. Or you can also think about it as an embedding notion for a graph, where embedding is understood in terms of first order logic. Good, so FO transductions. So an FO transduction consists of, okay, maybe before I tell you about FO transductions, I will give you a very basic notion of an FO interpretation. So imagine that I've got some formula phi with two free variables, x and y. This is a symmetric FO formula. And symmetric, I mean that it always is the case that phi of xy holds if and only if phi of yx. Yeah. Then if I'm given a graph G, I can apply this formula to my graph G, getting a new graph which I call phi of G. So what is this graph? This is a graph on the same set of vertices, but I reinterpret the edge relation. I put the edge relation in my new graph whenever phi tells me to do it. So I will put here all the edges UV, such that in my original graph G, phi tells me to put an edge. Yeah. So okay, that's kind of a bit weird, maybe at first glance, but maybe some examples. Yeah? So if my phi xy is just that there is no edge between x and y, yeah, then what happens here? I'm putting an edge whenever there was no edge, right? So this is the same, then phi of my graph G is just the complement, right? Okay, another example. So imagine that my phi of xy is distance at most 2. Yeah, so I'm putting now an edge whenever the two vertices are a distance at most 2 from each other. So then phi of G is just so-called a square of a graph. So a graph on the same vertex, that's where I'm putting an edge whenever the distance between two vertices is supposed to. Yeah, so this is a way of taking one graph and deriving another graph through describing the new edge relation in logic. So that's a basic notion of first order interpretation. So now first order transduction.
You allow loops here, right?
Say distinct x and y. I don't want to think about loops. In general, I really don't want to go into technical details in this talk. Yeah. But yes, the fact that we are working with graphs, actually, this can point to a relevant remark that we are now here working with the notion of graphs, which are just one binary symmetric relation, which is a very basic kind of objects, but we could also work in relational structures with relations with higher arity than 2. Typically, whatever I'm doing here will work quite nicely in binary structures, so where all the relations have arity at most 2. There are problems in many arguments if you want to go to higher arity, and this is an unexplored area so far. Good. Okay, so now first order transaction. It consists of a palette of colors, a finite palette of colors, let's call it P, and also a formula phi that works on P-colored graphs. Yeah, so my formula phi can not only speak about there exists a vertex, but it can say there exists a blue vertex. Yeah, or for every red vertex there exists a blue neighbor, and so on. Yeah, so this formula can also speak about this colors. So now if I want to take I have transaction T. So if I have a graph G, then I can apply my transaction T to G and get a set of all graphs obtainable as follows. So now, even though we had applying a single formula to a graph was kind of deterministic, you know what is the result. Here, instead of having one single output, we will have multiple different outputs. Yeah, so a transaction is inherently a non-deterministic process. You can think about this. So all graphs obtainable as follows. So first, color G with P, anyhow. Yeah, so let's call the new graph G plus. Then apply my formula phi. So in this way, I get graph phi of G plus. Yeah, and third, take any induced subgraph. Yeah, so just remove any subset of vertices. Yeah. So in this way, in point 1 and point 3, I have a choice of how I color and how I take an induced subgraph.
In the resulting graphs, you still have colors?
No, in the resulting graph, I drop all the colors. So this takes an uncolored graph and outputs an uncolored graph. So for instance, example. So example, which will be also a definition that I will need later. I will say that H is a bipartite graph. Is a semi-induced subgraph of G if the following holds. If I can take G, find some two disjoint subsets of vertices, and then the semi-induced subgraph that is induced, semi-induced by those two is the bipartite graph consisting of all the edges in between. Yeah. So then there is a transaction that outputs all semi-induced subgraphs. Yeah, why? Because I can, using two colors, green and pink, I can choose two subsets of vertices. Then I can say in my phi, I retain only edges that have one endpoint green and the other endpoint pink. And then I drop all the other vertices that were not colored green or pink. Good. So in this way, now T of G consists of all the semi-induced bipartite subgraphs. Right. So now that we have the notion of transduction, you can think about transduction as sort of an embedding notion for classes of graphs. So first of all, I can, if I have a class of graphs and I have a fixed transduction, I can apply a transaction to a class of graphs and just do it pointwise, right? So this is the union of T of G for every G in my class. Yeah, so these are, you can think about it, T of C are all graphs that are encodable using this fixed mechanism of T in colored graphs from C. Yeah? And I will say that a class D is transducible from C if D is contained in T of C for some transaction. Yeah. So you should think about it as follows. D is transducible from C if every graph from D can be encoded using this fixed mechanism in some graph from C. Yeah? So maybe an example, every graph class is transducible from the class of its complements by just taking the transaction that takes the complement of the graph. Actually, the class and the class of complements are sort of transaction equivalent because I can go from D1 to the other and from the other to the first.
Could it be that you need to use two graphs from C to build D, and then it's not just from one graph, but
Well, that's not what the definition says. I'm not sure how to interpret your question.
It's subset T of C, but T of C is the union of over all G in C.
Yes. So this means that this inclusion means that every graph from D, for every graph from D, there exists a graph from C, such that I can get this graph from D from a coloring of the graph from C. Okay, I will denote it as follows, that D is smaller or equal in FO from C. And because transductions are composable, like composition of two transactions is transduction, actually this is a partial order on classes of graphs. Okay, so now that we have this notion of encoding one graph in another graph, or rather getting one class of graphs from another class of graphs in first order logic, I can define the two notions that we will be speaking about. I will say that C is monadically dependent. You can also see in literature monadically NIP. If I cannot transduce all the graphs from C. So in other words, whatever transduction I fix, whatever mechanism of getting one graph from the other I fix, I cannot obtain all possible graphs from C. So this is like a basic notion, like excluding some minor. Yeah, you exclude something for every fixed mechanism. And second definition, which is more restrictive, and this is the definition that we will be speaking about later, C is monadically stable if half graphs cannot be transduced from C, where a half graph is a graph that looks like that. It's a bipartite graph. That has two sides, A1 up to AK, B1 up to BK. So this will be a half graph of order K. And the rule is that, say, A1 is connected to all the Bs. But A2 is connected only to the subsequent Bs. And A3, the same. So in other words, AI Bj is an edge if and only if I is smaller or equal than J. You should think about a half graph as sort of a combinatorial description of a total order. So in other words, monadically stable classes of graphs are graphs where you cannot, where in colorings of those graphs, you cannot logically express arbitrarily long total orders. So in a sense, logically, they are orderless graphs.
That reminds the notion of stability in model theory.
Yes, that is actually not a surprise, right? These notions are not our notions. Monadic stability and monadic dependence, like stability theory is an established field in model theory. And in particular, monadic dependence and monadic stability, this was introduced in the 80s, I think, and there is a paper of Baldwin and Shala that describes properties of those classes, and this is a well-studied notion in model theory. Here, typically, there you are thinking about infinite models, and you are thinking that a single model is stable or is dependent. Yeah. Here, this is a projection of these notions to the finite, to the classes of finite graphs.
All your graphs are finite, right?
So far, yes. Yes. Yeah, so in particular, every class that is monadically stable is monadically dependent because I exclude something more. I exclude even this kind of graphs. Here, I just want to exclude some kind of graphs. Yeah. So what can we say about these two notions compared to the picture that is there? Maybe I can now move to this. So first of all, what is proved in the paper by Bonnet et al. In paper Twin with 1 is that classes of bounded twin width are closed undertaking. In the sense, if I take a transaction of a class of bounded twin width, we still have bounded twin width. The same goes for bounded twin width. Yeah, and in particular, not every class has bounded twin width, which means that classes of bounded twin width are monadically dependent. And because if one of them was not monadically dependent, I would apply this transaction, I would get all the graphs, but all the graphs do not have bounded. Yeah. Okay, so that's the first theorem. And another theorem of Adler and Adler, which dates back actually to an old paper of Podewski and Ziegler, is that classes that nowhere dense classes are actually monadically stable. And moreover, this is by Zenek-Dvořák, by a result of Zenek-Dvořák. Moreover, if you take monadically dependent and you intersect it with weakly sparse, so you consider weakly sparse classes that are monadically dependent, that's the same as monadically stable intersection weakly sparse. And that's exactly the same as nowhere dense. So in some sense, taking this projection of restricting attention to weakly sparse classes collapses these two notions to a notion that we already understand. So going back to this diagram, I can draw here the box corresponding to monadically dependent classes. And draw here in blue classes that are monadically stable. And have it like that. And now the conjecture that we are thinking about for the last few years is to prove that on every monadically dependent class, or at least on every monadically stable class, first order model checking can be done in fixed parameter time. And so far, what this talk is about is to try to understand these concepts, not through those abstract definitions from logic, but to try to derive combinatorial tools to understand those classes, to see some kind of decompositions on which you can start to, I don't know, apply dynamic programming, for instance. So looking at this diagram and seeing this monadically stable box here, it is also natural to think about how is there a row here. Yeah. So for example, you could think about stable classes of bounded twin width. Or stable classes of bounded clique width. Yeah, or stable classes of bounded linear clique. And classes of bounded Schroeder are actually stable, so you have a collapse here. So this is what we will not talk about during this talk, but there is a very nice line of research on understanding this column, this row of the picture. And in particular, what is known about these boxes is that, for example, stable bounded twin width is the same as transductions of bounded sparse twin width. Yeah. So in other words, whenever I have a class of bounded twin width that is additional monadically stable, in fact, you can find some kind of a skeleton, a sparse skeleton from which you can transduce it. And the same happens here, and the same happens here. Yeah? That every monadically stable class can be transduced from a lower dense class. That's a conjecture that is a very good conjecture, and we have no idea how to approach it. If this was the case, it would be amazing. Good, but this is not what we will be speaking about. What we will be speaking about for the remainder of this talk is about this box and trying to understand this box combinatorially to prove a combinatorial characterization of monadically stable classes. And so far we have two characterizations like that. One is called flip wideness and second is called the flipper game, and the title of the talk. And I will talk about the flipper game. And the idea is that these two characterizations are sort of exact lifts of characterization of lower dense classes. And this is why we think that this is a good notion, because sort of you understand characterizations here, you replace one component with another component, and you see characterizations there. Yes?
So we know that first order model checking is a fixed parameter tractable in lower dense classes. Does this imply that transductions of lower dense are also fixed parameter tractable?
That is a very good question. It doesn't imply it immediately because, like, the question is, how do you get the graph? You can get the graph by taking the pre-image, like this lower dense graph, and knowing the transduction, and then it's true. Because you can take your property that you would like to test in the output of the transduction. You can sort of pull back the formula through the transduction and do model checking on the lower dense pre-image. But this is not the actual question. The actual question is you got only the output of the transduction. Yeah, and then finding the pre-image is a computationally hard problem. However, there has been a progress on this front as well. So these classes are called structurally lower dense. These are exactly the transductions of lower dense classes. And there is an ongoing work that I probably shouldn't talk about much more on trying to get first order model checking. Yeah, but very good question.
Structurally lower dense is known to be a subset of monadic stable, and
yes,
maybe it coincides.
Yes.
Okay.
So the conjecture that you are asking about is exactly that. That monadical stable is equal to structural lower dense. Yeah. Good. And what is proven is, for example, that structurally bounded sparse twin width is equal to stable bounded twin width. That's something that we proved last year. Good. So as you see, this diagram is actually super interesting in my opinion. Like there's a lot of room to play with about this. Like for example, what should be the dense analogs of excluding a minor? Yeah, is it vertex minors? Not sure. What are the dense analogs of bound expansion?
The model checking thing in the column of twin width is true all the way down, yes?
The model checking, currently the model checking is like this. So, with the caveat that here we can do model checking if we have the proper decomposition, and a proper decomposition, we don't know how to compute it.
And for click width, you're doing
yeah, for click width, well, you need the decomposition, but you know how to compute it at bit time. For twin width, we do not know how to do it.
Stable twin width?
Well, if for stable twin width, we also a good question. I don't think that we know how to compute the decomposition. I don't think so.
So there is also the capital
there. Yes.
and sparse twin width?
Well, that's nowhere dense.
That's nowhere dense.
Yeah. Or even bound expansion. Good. Okay, so I'm very happy that you are interested in this diagram because I find it remarkable. But now we are going to talk about the notion of monadic stability and how to combinatorially describe monadically stable classes. And as I said, the characterizations that I will be speaking about is a generalization in some sense of a characterization of nowhere dense classes. And the characterization of nowhere dense classes is called the splitter game. So I will now divide this board into two halves. Let's say halves. And here there will be splitter game and there will be splitter game. So the splitter game is a game played on a graph. There is a fixed parameter R, which is the radius of the game. Yeah, and there are two players. One player is called splitter, and the second player is called connector. Yeah. The game is played on a graph. So there is always an arena. A graph, originally some routing. But the arena will shrink during the game. So you should think about the arena being sort of fluid. Good. So how does a round of the game look like? How does it look like? So here is my current arena. Yeah. So the first move is a move of connector. Let's say connector. It doesn't really matter. So connector first localizes, or rather is forced to localize. So localize means that picks a vertex, say U, in the arena, and the game is restricted, arena gets restricted to the ball of radius R around this vertex. Yeah, in the current arena. Yeah, so typically what connector would pick is some sort of a central vertex U to gather as much as possible, because connector tries to endure in the game as long as possible, and then the game is restricted to this ball. Yeah, so everything here gets removed from the arena. Yeah, and now is the turn of the splitter. So splitter removes any vertex V from there. Yeah, so here is some vertex V. Splitter just removes it, so the arena now looks like that. Yeah. So now in the next round, again, connector will pick a vertex, another vertex U, and the arena will be shrunk to that. Yeah. And splitter will again remove a single vertex, and so on. Yeah, so the goal of splitter is to finish the game as quickly as possible. The game finishes when the arena is empty, and the game of the goal of connector is to endure as long as possible. So now a theorem of Goeckhoys and Sibats is that if C is nowhere dense, if and only if, for every radius R, there exists a bound L of R on the length of the game, such that splitter can win in at most L of R rounds on every graph from X. Yeah. So the characterization of nowhere denseness is that for every R, the game is shallow. Yeah, I can have a uniform bound on how many rounds I need to clean the whole graph. And you can think, and that's actually a convenient way of thinking about the splitter game, that the splitter game is kind of a hierarchical decomposition of the graph. Because it's it's a hierarchical decomposition to smaller and smaller vicinities, where a vicinity is what is the move of the connector. And then I get an additional move of splitting the graph using some kind of a central vertex that the splitter chooses. Yeah. So in some sense, this means that nowhere dense classes have this kind of shallow hierarchical decomposition to smaller and smaller vicinities. So that's a splitter game. And this theorem of Goeckhoys and Sibats, it was a sort of cornerstone of their model checking algorithm for nowhere dense classes. So now I will introduce the analog of this, which will be called the flipper game. And again, there will be a radius of the game. Actually, the game will be very similar. There are two players. Again, there is connector. And the second player is now called flipper. Again, there is an arena, which is a graph. It's originally some graph G. Yeah. And the round looks like that. Yeah. So here is my arena. So first, connector does exactly the same as the last time. So connector localizes. So in other words, picks a vertex U, and the game is restricted to a ball of radius R around. Yeah. Note that I still use the normal combinatorial notion of distance in the graph. But now what flipper does, flipper applies a flip. And what is a flip is he chooses some subset of vertices and complements the edge relation there. Yeah. So in other words, he chooses here some subset of vertices, X, and replaces all the edges with non-edges and vice versa inside here. Yeah, so this is how we change the notion of removing a vertex into the notion of applying a subset complementation. Yeah. And the game now finishes when the arena finish if the size of the arena is one vertex. And because now flipper doesn't have ability of removing a vertex. So actually, there's no possibility of making the arena totally empty. We just define the end line when the arena has one vertex. And now the theorem that we hopefully managed to prove is that C is monadically stable. What we expect. If and only if for every R, there exists a bound L of R on the length of the game, such that flipper can win in at most L of R rounds on any graph from class. Right? So observe that this is a purely combinatorial description. There's no logic inside. Yeah? We defined monadic stability through this crazy transaction stuff. Yeah? But now this is a purely combinatorial decomposition theorem. Good. Any questions at this point? Because now I've stated the main result, and we'll proceed to sort of sketching at least a little bit of a proof. Yes.
So in lower dense classes, how can we get splitter strategy from flippers?
Very good question. It was the next point on my list. Actually, observe that. Like this flips is a kind of a robust notion. I can also think about not just taking and making a flip, but I can also make a sort of bipartite flips. If I have two sets of vertices and I would like to complement the edge relation between A and B, I can do it in three flips. Flip A, flip B, and then flip A union B. Yeah. So within 3 rounds, I can do a bipartite flip. And observe that actually both the splitter game and flipper game is kind of robust with respect to doing things one at a time, in the sense that if I would like to make 3 flips, I can do 3 flips in consecutive rounds, and the localization of connector can only help me. So I can think about that I'm not doing just 1 flip in a round, I can do several flips in a round. As long as it's a bounded number, it's okay. Yeah. So in this way, I can do a bipartite flip in a single round, sort of. And now if you think about the splitter game, removing a vertex, you can think about as isolating it. So removing all the edges to its neighbors. And this is a bipartite flip between a vertex and its neighbor. Yeah. So in this sense, the flipper game generalizes a splitter. Yeah. And this is very nice because it corresponds to monadic stability generalizes nowhere. Right, but that's a very good point that actually both in the splitter game and in the flipper game, I can think about flipper or splitter making several moves, removing several vertices or applying several flips in a single round, as long as this is a bounded number. Yeah, because he can just then apply them once at a time in several consecutive rounds. Do I have more? No, I don't think that I have more here. Yeah, so the remainder of the talk is about telling you a little bit about the proof of this theorem. I have sort of half an hour, so I will definitely not go into very much detail, but I would like to at least sketch the core arguments in there. We have 2 proofs of this theorem. I will tell you something about only one of them. So let me first say a little bit about the other proof. So there is an algorithmic proof and a model theoretic proof. So the algorithmic proof it starts from a notion called flip wideness. Which is, if you know something about about lower dense classes, you know perhaps that there is a characterization using uniform quasi-wideness, which essentially says that if you have a huge lower dense graph, you can remove a bounded number of vertices so that you see many vertices far from each other. That's in essence uniform quasi-wideness. Now, flip wideness is a direct translation of this to the sort of flip setting, in the sense that in a monadically stable graph, or rather a graph from a monadically stable class, you can apply always a bounded number of flips to have many vertices far from each other. You just take the definition of uniform quasi-wideness, you replace the notion of removing a vertex with the notion of applying a flip, and you get the notion of flip wideness. So if you have this notion of flip wideness, then you can give a strategy for flipper. I will not tell you more about the strategy. If you know how splitter game, how this theorem of Grover-Croizon-Sieberts was derived from uniform quasi-wideness for lower dense classes, it is sort of a repeating this kind of an argument, but just having flip wideness is not enough. You need to strengthen this flip wideness with a certain sort of predictability, whatever this means, property, which is a non-trivial piece of work. And then using this predictability property, you can sort of apply a similar scheme to get a strategy for flipper. And a particular thing that you can derive out of it is that there is an order of n square algorithm to compute the next move. Yeah. So this is already very nicely suited for doing model checking, right? Because this decomposition is algorithmic. Yeah, you know how to decompose it further. Yeah, you can compute it. So this is a proof that I will not talk about, because talking about this would be a little bit boring, because I would need to introduce flip wideness. I would need to make you believe me a result of Dyer, Sieberts, Stojanczyk, and Malman, that flip wideness is an exact characterization of monadic stability. So a class is monadically stable if and only if it is flip wide. Yeah. So then I would, from flip wideness, derive the strategy for the flipper. So it will be deriving magic from magic in some sense, so which is not that satisfying. I will instead try to tell you a little bit about the other proof, the model theoretic proof, which gives you absolutely nothing in terms of algorithm, yeah? But it is kind of cool anyway. And in particular, on the way, it gives you some additional properties of monadically stable classes that I guess are of independent interest, in the sense that it gives you more insight into kind of structural properties of those classes. So the sort of sketch of the plan is to start with monadic stability. Then from monadic stability derive some notion that I will call separability in elementary extensions. Which is a property that is purely in the language, in the setting of infinite models. Like, it makes no sense in the finite. Yeah. From this, I will derive a strategy in a different game. So separator wins. Separator game. There will be another variant of flipper game that is more suited to actually work with it. And from separator wins in the separator game, I will derive that flipper wins in flipper. So this gives you one implication from monadic stability to to the flipper game, which is probably the interesting implication. To derive equivalence of monadic stability, you need to work a little bit more about using obstacles for monadic stability to give a strategy for the connector. Good. So I will almost not tell you anything about this implication because it's boring. It's just a translation of one strategy to the other. It's technical. In essence, this implication I will sketch probably at the end, if time permits. It's obtained using compactness argument. So in a sense, we will have some kind of model theoretic notion here. And assuming that connector has a possibility of evading separator for longer and longer periods, we will construct through compactness a model where he can avoid losing the game for infinitely many rounds, and this will be a contradiction with this notion. And the crux of the proof is here. So I will be mostly speaking about this. Okay, separability and elementary extension. Good. Yeah, I will actually leave this board here because maybe at the end there will be some questions and this board will be interesting. So first, we need a few definitions, I guess. So imagine I've got a graph G. From now on, all the graphs can be infinite. Imagine I've got some graph G and I have some subset of vertices S. Then I can define something that I will call S classes. So partition G, or rather the vertex set of G, into S classes. What is an S class? So here I've got my graph G. I've got some small set of vertices S. Yeah, and every vertex of S is in its own S class. And all the other vertices are partitioned according to what they see in S, according to simply their neighborhoods in S. And so here I've got this partition into those boxes according to the neighborhoods in S. Yeah. So in model theoretic terms, these are edge relation types on S. Yeah, so these are S classes. So an S flip, observe that if S is finite, then the number of S classes is also finite. Yeah, it's something like S plus 2 to the S. Okay, so then an S flip is a set of flips, bipartite or not, between S classes. So for example, given this S classes, I can say that I will flip this box against this box. So I will flip the edge relation between those two boxes. And I can, for example, flip between this box and this box. And maybe I can flip this box with itself in the sense that complement the edge relation here. Yeah? So this is a kind of a flip that is definable or governable by a finite set of vertices. Yeah? And again, the number of different S flips is again finite, assuming the set is finite. And because simply for every pair of boxes, I will tell whether to flip or not. Yeah, so that's an S flip. So given that, I can define a metric, sort of a metric on the graph. It will, you can view it as a metric, but maybe this is a too large word for this notion, I will say that if I have two vertices U and V, maybe let's draw them somewhere, U and V, I will say that U and V are separated by S if in some S flip we have that the distance between them is larger. So this is a notion of separability in this flip context, in the sense that U and V are separated by S. If I can perform some flips definable through S, so that U and V end far from each other. So I will then note this notion as follows: U anchor over S at distance RV. So that's the notation. And if you know something about model theory or stability theory, you will recognize that this is a notation for forking independence. And that's not a coincidence. Actually, it turns out that this notion of separability can be used to characterize forking independence in monadically stable classes. But I will not go into the details here because this is an ongoing work that I'm not involved. So I'm just stating that there is a connection here, and it's actually hopefully a deep connection. But so far, this is like purely combinatorial. Okay, so that's our separability. So now I need to define this separability in elementary extensions. And for this, I need to tell you about what is an elementary extension. So if I have two graphs, G and H, so the picture is I've got a graph G and I've got a larger supergraph H. So elementary extension, you can think about it as sort of a generalization of a notion of an induced subgraph. This is how I think about it. It's a generalization towards like respecting not only like induced edge relation, but actually all relations that are definable in further relation. Yeah? So these are two infinite graphs. G is a subgraph of H, actually an induced subgraph. And this is an elementary extension if for every formula phi, say X bar, Y bar, these are tuples of vertices. Maybe actually this will be some tuple of vertices from G. Yeah, so imagine that here I've got some tuple of vertices M. Yeah. If there is a witness in H, then there is also a witness in G. Yeah, so if there is some kind of way of finding a tuple of vertices N such that phi falls between those two, then actually I can pull these guys here. I can also find witnesses already within G. Yeah, that's the notion of elementary extension. In particular, if
Tarski criterion, right?
Sorry?
That's Tarski criterion.
That's Tarski criterion. I will use Tarski criterion later. I will actually not use because I do not have time, but yes.
So this definition is saying that this holds for all entities.
It holds for all formulas. Yes.
Yes. Okay. Yes. For all choices of these constants.
Yeah, of these parameters. Yes. Whenever you have a tuple of vertices here, yeah, and you have witness there, then you can also pull a witness here. Yeah. So for instance, if my formula says these guys have a common neighbor and there is a common neighbor in the whole graph H, then there is also a common neighbor in the graph G.
But the formula phi is also allowed to have arbitrarily many of these variables.
Yes. Good. So that's an elementary extension. And in particular, observe that if I take X to be an empty tuple, I say that phi is satisfied in H if and only if it's satisfied in G. So in particular, this says that the theory of G is the same as the theory of H, or the theory of a set of sentences is satisfied. Okay, so now the definition of separability, maybe as a theorem. So imagine that I've got G and H. This is an elementary extension. And say that they both belong to some monadically stable graph cos. Well, in the actual proof, we need to have a slightly weaker notion here, but yeah, that's a detail. Good. Then, for every vertex U that is outside of G, here I've got some vertex U. Yeah, I can sort of nicely separate it from G in the following sense. For every vertex here, there exists a subset of vertices S inside the G, which is finite. Yeah, so I can find here a few vertices S such that U is separated from G over S up to R, then for every R. So in a sense, I can pick here a few vertices and choose a flip definable from those vertices so that U becomes far from G.
That means from every vertex in G.
From every vertex in G. That is this notion. So I will definitely not be able to tell you more here, but in essence, there will be a notion of a separator game where the separator will build larger and larger sets of vertices that will be governing sort of flips. And using compactness, we will say that if the connector can evade end of the game indefinitely, there will be some model where it can actually do it for an infinite number of rounds. And the fact that there would be a vertex here that will be still in the arena after omega rounds, but outside of some kind of a model that separator built during his game, because separator will be actually building a model, there will be a contradiction with the fact that this guy is still in the arena, but can be finitely separated from G. Essentially, this is the point here. Yeah? But now I will try to tell you a little bit about the proof of that. Okay, so we need to prove this for every R, so let's start with R equal to 1. And actually R equal to 1, perfect, Jeff, okay. R equal to 1 is a property that's actually well known in model theory, in stability theory. And it's called the finability of types. So a theorem says the following. So imagine that G and H are elementary extension. And they have both stable edge relation. Stable edge relation means that I exclude some half graph as an induced subgraph, as a semi-induced subgraph. Yeah, that's the only property that I need here. Yeah. Then for every vertex U in H minus G, so the picture, here is G, here is H, here is U. Yeah. And I'm thinking about the neighborhood of U. The neighborhood of U intersection G, so everybody that can be seen here, can be expressed as a positive, as a finite positive Boolean combination of neighborhoods in G. So what does it mean? It means that I can find here a finite set of vertices and look at their neighborhoods. And write a positive Boolean combination of those neighborhoods to exactly get the neighborhood of U. So sort of every neighborhood from the outside can be pulled inside G by expressing this neighborhood not by a single neighborhood, but maybe several of them. Yeah, it's actually kind of a majority vote in some sense throughout the neighborhoods of several. So that's a known theorem. It's called the finability of types. The proof is actually not that hard, but I will not be able to tell this within the next 5 minutes. The idea is that you sort of try to make better and better approximations of the neighborhood of U through the neighborhoods within G. So there is a kind of an algorithm that makes better and better approximations. And this algorithm sort of at every step of getting a better approximation builds another rung of a half graph. So the algorithm actually needs to finish within a bounded number of steps because otherwise it would create a too long half graph. Actually, the truth is that I actually have two procedures like that within the proof, but anyway. So now if I have this theorem, the case R equal to 1 is actually very simple because this will be my set S. Yeah. So in other words, if I have my set S here, and I think about S types, they look like that. They partition somehow the whole graph, both G and H. Yeah. And what I know is that if I take U and I take the neighborhood within G, it's just a collection of S classes. That's exactly this can be expressed as. Yeah. Which means that what I will actually do, I will flip the class of U against all the classes that contain its neighbors. And in this way, I will dispose of all the neighbors of U within G. So having this R equal to 1, okay, now we can go to the case of R larger than 1. I will try to just show you the key trick. So we have here my graph G. Here I've got my vertex U. Yeah. And by applying induction for R minus 1, I can already do it using some finite flip definable from G. I can make U already like R minus 1 distant from G. So if I draw a ball of radius R minus 1 around U, it is disjoint with G. It's only that the sphere, the vertex at distance exactly R minus 1, can have some neighbors in G. And I would like to dispose now of this connection. Yeah. Good. So let me look at this bipartite graph here between the sphere and the G. So there are 4 cases. Case 1 is that this graph, so this, let's call this bipartite graph, I know, J. J has, I will call it few types. In the sense that if I think about the neighborhoods between here and here, okay, maybe the rank of this bipartite graph is actually small. There are only few neighborhood classes of what people from here see within G. If there are only few neighborhood classes, then we can sort of apply case R equal to 1 to those neighborhood classes. To each of those neighborhood class can be described using a bounded number of vertices, a finite number of vertices. They all constitute my set S. And now using this union, I can flip away those connections, roughly speaking. Yeah. There is much more technical details actually here. I'm hiding quite a lot of tricks inside this. Okay. Second case is that J has an finite number of times, has an infinite matching, induced matching. Yeah, so I can actually see here an induced matching looking like that. Third case is a symmetric. G has an infinite co-matching. Yeah, so a complement of this. And the fourth possibility is that J has an infinite half-graph. So this is a very nice purely combinatorial lemma saying that every bipartite graph has either finitely many types from one side to the other, or has an infinite matching, or an infinite co-matching, or an infinite half-graph. So this case is definitely excluded, right? Because we are stable. Yeah, this case we already have sort of done. These two cases are symmetric, so I will focus on this. Yeah, so and now the picture looks like that. And I claim that now this case actually leads to that the graph H is not monadically dependent. I will show how to transduce any graph from it. So let me fix some graph say X on n vertices. And by restricting attention here to a set of size n, I can imagine that here I've got n vertices and here I've got an induced mesh of size n. Now the idea is that now this whole, I will call it a rocket. Yeah, this rocket is of bounded size. It has size at most n times r. Yeah, because the length of this is r. If I just, for each of those vertices, I just fix one path to it. Yeah. So now the existence of a rocket like that is something that I can express in a flow in first order logic. Yeah, it's just that there are vertices having this kind of a pattern. So if this is true in the whole graph H, because of the elementary extension, it's also true in the graph G. So there is also a rocket like that. Yeah. But now there are two rockets in H. This rocket and a disjoint this rocket. This can also be expressed in first order logic. So it is also true in G. So actually in G, I can find two rockets. And the same trick, I can find three rockets, and so on and so on. Yeah. So all in all, I found n vertices here, and as many as I like, rockets looking like that. And if you stare on this picture long enough, you can actually see that the rockets are disjoint. They have induced matchings here. And the bodies of the rockets are like, the body of every rocket is not adjacent to any other rocket. You need to apply a rounding here, but to get it. So now this kind of structure is already enough to be able to transduce any graph from it. Because if I would like to transduce a graph X here, and I would like to say that these two vertices are adjacent, make an edge between these two guys, I will pick one rocket. I will look at the two vertices corresponding to those guys here. I will color them using, say, a blue color, and I will color a path within here using a green color. And for every edge of X, I choose a different rocket here to realize this edge. And now my transaction will say two vertices of this set of n vertices are adjacent if and only there is a path between them that starts with a blue vertex, goes through some green ones, and finishes with a blue vertex. And that's contradiction of monadic dependence. Okay, so that's this basic, well, not basic maybe, but this strategy of building those rockets and using this as a sort of a obstacle for monadic dependence. If you look at the model theoretic literature, actually this construction is called making a Morley sequence. Morley sequence. Good. So I think that I've shown you sort of the main trick how to prove the first step in this chain of implications. For the other step, we would need to use compactness to use this this notion to prove a winning strategy in the separator game. From the separator game, I would need to go to the flipper game, which is just a technical translation of strategies. Good. But that's the core. So maybe some 2 sentences of conclusions. So far in this picture, we understand monadically stable classes through flip wideness and through flipper game. These are 2 characterizations that generalize splitter game and uniform quasi-wideness, respectively. In order to get model checking on for first logical monadical stable classes, what we are lacking is another ingredient that was used in Grecois and Siebert in the lower dense setting, which is called neighborhood covers, whatever this is. And there is a prevailing intuition that in order to get those neighborhood covers, what we will actually need to understand is analogs of so-called generalized coloring numbers in this monadical stable class. And this we are lacking. This we are lacking for already a few years, and we're trying hard to understand what should be the analogs for generalized coloring numbers. And if we get this, hopefully a lot of stuff about this picture will be better understood. Okay, I'm sorry that I made it a little bit longer, but I hope that you liked it. Thank you.
Thank you.